Hello everybody, welcome to a new video on the channel. The first video of a four-part series where we're going to dive into cosmic dynamics, but we're going to simplify it to a high school level, such that it's able to be understood by high school students. Why do I say simplify? Because cosmic dynamics, or even cosmology in general, deals with many concepts that high schoolers don't typically understand, nor do they study. So we're going to simplify it in order to be understood. So the first part of all of this is the Friedmann equations. Now what is this? These are equations that can help us to understand the expansion of the universe. We can see in this diagram here that there have been observations that prove that the universe is expanding. The one you hear about most is probably that all galaxies are receding away from us everywhere. Well, not all, but far galaxies on the cosmological scale, yeah, they're moving away from us. Why is that? Well, we must return back to the fact that the universe is everything that ever was, everything that is, and everything that ever will be. Therefore, by saying that the universe is expanding, we're saying that space itself is expanding. It might be hard to wrap around. So an example that you can take is by plotting dots on a balloon and inflating it. So relative to other dots, that if you pick a certain dot, it will seem like that dot is moving away. But relative to the balloon, it doesn't. So it just seems like it's moving away because of the entire balloon getting bigger, making it seem like it's moving away. And because of that, we can then get something called the scale factor. So how do we visualize it? Here's a way we can visualize the scale factor. Now, these are wavelengths of light, and we can compare them. The one on top is the original light, the light that is emitted by stars or quasars or other objects, and the light below is the light that is observed. So you can see that these wavelengths or these photons, they change, right? The one on top is blue, the one below is red. The one on top has shorter wavelengths, the one on the bottom has longer wavelengths. And you can also say inversely about that, about its frequency. Now, why does this happen? Well, you can see in the explanation here that the universe expands with time. So when light travels, it's kind of, the wavelength is kind of stretched out by the universe as well, it's kind of elongated as well, such that the original blue light with shorter wavelengths and higher frequencies becomes stretched out to be red light with longer wavelengths and smaller frequencies. Again, this stretching out happens not because of the object moving in relative to itself. It happens because of the universe's expansion, or what we call cosmological redshift. So scale factors, the scale factor is just the wavelength of, the wavelength of the red divided by the blue. So the longer objects travel through time, the more red they become, the bigger their scale factor is. So now let's try to derive this. As I've mentioned earlier in the disclaimer, we're going to use many simplified theories, such as we're going to see that we're going to use the Newtonian theory instead of general relativity, because that's not generally taught in high school. And we're also going to see simplifications that are based on facts, mainly that the universe is homogeneous and isotropic. So let's begin with stating that the total energy in the universe is comprised of its kinetic and potential energy. That kinetic energy being the movement of particles and the potential energy being the gravitational energy, mostly dominant in larger scales. So you may see this and think that it's rather common, right? So yeah, we're basically going to take the this example here, the universe, or everything inside the universe in one single block right here, and we're going to take an imaginary object right here. And of course, that object can't be real, because if everything in the universe is over here, how can there be something over there, right? But we're just, for the sake of simplification, just assume that's it. Then we've expanded that, and remember what I've said earlier about the scale factor. So what happened here? Well, just so we're saying that distance, or the current distance, or the radius of the universe, scale factor multiplied by x. One thing I forgot to mention about the scale factor is that the distance of objects change through time, such that you really have to tell when a measurement was taken in order to say that it was done precisely. And to do that, you must tell the era and the scale factor during that era compared to the one right now. So we're just going to simplify it in the beginning here, such that r here is equal to ax. And remember, mass is just volume multiplied by the density. Again, we're going to assume that the universe is a sphere, such that the volume is 4 pi over 3 r cubic, or in this case, ax cubic. And we also have to take fact that velocity is just dr over dt. And because r is equal to ax and a is a function of t, or scale factor is a function of time, so yeah, you can just derive the scale factor and by the time. You can get the velocity. And then let's just simplify it more. So basically, for notation purposes, so just to make it more easily readable, so whenever you have d anything over dt, it's just that thing with a dot on top. So and the next, we're going to move the potential energy to the other side along with the total energy. Why so? Well, in order to keep it all positive. And that's the first purpose. Another purpose we'll see later in the equation. Then we're going to multiply everything by 2 over m a squared over x squared. Now what does that do? That cancels out 1/2 m x squared, and puts an a, you can say puts an a under this a dot, such that it will be a dot over a squared, which is the change in scale factor divided by the current scale factor squared. Or another way to put it is the Hubble's constant squared. Right? And one thing that you're gonna see from here is this thing, 2u over mx squared, which is equal to negative kc squared over r squared. What do these variables mean? C is just the speed of light squared, and r is the radius of the universe. Radius of the, yeah, I think the radius of the universe. Now what about this k here? Well, the k is just stating the curvature of the universe. We'll dive into it later. Right now, all you need to know is that k is equal to the curvature of the universe, which is dependent on the energy of the universe, or the component energy of the universe, such that we can restate the equation here. H null squared is equal to change in A over time divided by A squared, which is equal to 8 pi g rho over 3 minus kc squared over A squared r squared. Remember to put the A squared back in. So I've mentioned this thing called the curvature earlier, right? Which is dependent on the total energy. So what do I mean by this? You can kind of view the universe as kind of plane, if you will. Like I said, we're going to simplify like the balloon, and it can either have positive, negative, or flat curvature. Right. Positive curvature is when k is greater than 0. Negative curvature is when k is less than 0. And flat is when k is equal to 0. And if you relate it back to u, remember that u is proportional to negative k, or k is proportional to negative u. Therefore, positive curvature happens when u is negative, or the gravitational potential energy is greater than the kinetic energy. Negative curvature occurs when the kinetic energy is greater than the potential energy, and the flat curvature happens when they equal out. Now, why is this important? The curvature of the universe, what does it do? Well, it kind of determines the fate of our universe. So yeah, you can see it yourself over here in the bottom diagram. When the curvature is positive, the universe will expand to a certain point, where it will implode on itself in a way. It will compress itself all the way back to the single point it used to be. For a flat universe, it will expand to a point where the size will remain constant forever. This expansion will happen and will be slowed down until that size inevitably comes. And for a negatively curved universe, it will expand, and that expansion will be accelerated such that it just keeps on getting bigger and bigger until forever. So yeah, this is all for this video. I hope you enjoyed and learned something new. Thank you.